Okay, so welcome back to another video. Today's video is going to be composed of a algebra problem we will want to find the value of. So we're given that s is equal to cosine theta divided by 2 plus cosine of 2 theta divided by 2 squared plus cosine of 3 theta divided by 2 to the third power and so on. So as you see, we have an infinite sum that we're utilizing. And we're also given the value that cosine of theta is equal to 2023 divided by 2024. What is the value of capital S? So, of course, we notice that the first thing is that S is in the form of an infinite sum. So we'll have to, write some sort of generalization of a sigma notation that we'll put in there. And then we can actually notice something that actually will reduce down to that simplification. What that utilizes actually, we're going to have to get a little, go into a different world of number system. Specifically, we will be transforming this into using complex analysis. Well, complex numbers, really, that we will be, utilizing that. And then once we can do that, then we can actually just, use some complex number algebra to simplify some things apart. Then we just plug in our value for cosine of, of the given, and then we have our answer that we want to achieve for. So as simple as that. Today's video is going to be a quick/easy video. If depends on your definition of easy and loosely. So why don't we actually just jump right in? So first, S can be written in our following infinite sum over here. As you'll notice, we can start with our term as n is equal 1 to infinity of cosine of n theta and then divided by 2 to the power n. So in other words, what I can do is that transforming this into using complex analysis, we notice that cosine, if I actually take the real part of Euler's formula of e to the power I theta, we actually get the real part for cosine. And since everything is taking in parts of the real parts utilizing such that it equals the cosine function. So that means that, we can actually take the real part of the entire infinite sum over here. So that means we have the real of the infinite sum at n is equal 1 of e to the power I times n times theta, since it goes by each one for over here. So n and n times theta all being divided by 2 to the power n, then what we notice is that if we actually just look at inside of our infinite sum over here, so you'll notice that we can actually factor out the exponent for n, and so we have something of e to the power I theta divided by 2 to the power n. Doesn't this look familiar? This is actually something in the form of a geometric series. And of course, for the geometric series for the complex number, it actually still utilizes the same validity for a real number, such that the absolute value of, in this case for the complex number z, must be strictly must be strictly less than 1 for it to converge. Of course, this being the case, if I take what's inside of our parameter inside e to the power I theta divided by 2, and then if I take the absolute value of that, aka what we have is the modulus, so we know that if I convert the modulus, so the modulus of e to the power I theta, that's the same thing as taking the square root of cosine squared theta plus sine squared theta, equals 1. Of course, we have a divided by 2, so that means in this case we have 1/2, and of course that actually fits that validity such that it does converge since it is strictly less than 1. So applying the geometric series, and of course be careful that because our n equals 1 instead of 0, so we have to utilize the form carefully, utilizing its common ratio. So in other words, the geometric series by that justification, we have e to the power I theta, then divided by 2, divided by 1 minus e to the power I theta, and then divided by 2, which you can simply reduce this to just, e to the power I theta divided by 2, and then minus e to the power I theta. And of course, I should also write that the complex value for z is strictly less than 1. And then I'll put geo to, shorten it to say that this is the geometric series. Okay, so now continuing forward, that we can reduce this even more such that we have the real part of e to the power I theta and then divided by 2 minus e to the power I theta. Okay, so to, convert this even more such that we can actually continue with the simplification, why don't we actually write out its full formula? So that means cosine plus I times sine. So the real of cosine theta plus I times sine theta, and then all this being divided by 2 minus cosine theta and then minus I times sine theta. And you might be thinking, how can we actually continue on with this evaluation? So to reduce this even simpler, why don't we actually now just multiply its conjugate for both the numerator and denominator of our 2 minus cosine minus I times sine theta. At least we have the real part and the imaginary part. So continuing forward, that we have the real Okay, and so by multiplying the conjugate, so let's see, the numerator is going to be cosine theta plus I times sine theta. I should actually add a parentheses over here. Multiply its conjugate, so that means it's going to be 2 minus cosine theta, and then add this with I times sine theta. Okay, and then under the denominator, if I multiply its conjugate, we're going to get something in forms of a, a difference of squares over here. So we have a 2 minus cosine theta over here, then square that, and then add this with sine square theta. Okay, and then we can actually close out this parentheses over here. All right, now to continue forward with the simplification, we have now is going to be the real part. Now our numerator, so if you want to expand this out, you can. So I'll actually expand this out anyway, and then I'll get to, more details later. So doing so, we actually expand this out. So I have cosine of theta. So I'm not actually going to write the multiplication out in full. So I'm going to have cosine, then 2 minus cosine theta, and then add this with I times sine theta, and then multiply by cosine theta. Next, I have plus I times sine theta, all this being multiplied by 2 minus cosine theta. And then lastly, I have minus sine square theta. All right, so there must be a long one, so we have that. And then under our denominator, what we have now is that just expand this out. This one's pretty easy to do. So I have a 4, then minus 4 cosine theta. And then next I have a plus cosine squared theta, and then add this with sine squared theta. Okay, and then close this off. All right, so I didn't do the whole multiplication in full. Obviously, as we know that we're only just focusing on taking the real part of this entire thing. So that means we can just ignore all the imaginary, units involved. So this can actually just disappear. And so we're left with just that this is S is going to equal to, now we just take the real part, of course, so it's going to be cosine theta multiplied by 2 minus cosine theta, and then now subtract with sine squared theta, all this being divided by, so I'm actually just going to continue writing, so 4 minus 4 sine cosine theta plus cosine squared theta, and then add this with sine squared theta. Okay, and so with this, now we can just reduce things further. So that means I have a 2 times cosine theta over here, and now if I multiply the cosine theta over here, so it's a minus cosine squared and then a minus sine squared, so that means that's just going to equal to just minus 1, all being divided by, so let's see, cosine theta, sine squared theta, same thing, so that's a 1. So add this, so that means I have a 5 and then minus cosine, 4 times cosine theta. All right. So that's as simple as we can get. Now all we have to do is just plug this back into over here. So why don't we actually do that? So this leaves us with 2, then times 2023 divided by 2024 minus 1 divided by 5 minus 4 times 2023 divided by 2024. And then we continue forward. So we'll reduce this to just 1011 divided by 1012. That's just the numerator divided by, now do this multiplication over here and simplify. We have 507, then divided by 506. We can reduce this even further to yield us with 1011 divided by 1014. Simplify down even further to get that our final answer is that S is going to equal 337 divided by 338. And just like that, we have our final answer for S of this infinite series with a given cosine theta assigned to that, and then we can actually, deduce to this following. So you're not actually having to plug each one at a time. It's an infinite series, so that's why you got to, get to the nitty gritty and then, use what you know and then get to something simple as that. So yeah, that's pretty cool if you ask me.